Okay. Well, thank you for the introduction, and we can talk about relative ages later on, Danny, at the reception. I'm delighted to be here. It's a wonderful meet. Look at this, 120 people or more, maybe more. I've just browsed the program. We're going to see some fancy, modern modeling, computation, applications, typical of cutting-edge Bayesian research these days. And this is one of the world's major series of meetings in the community now. I'm very grateful to be invited to speak, and let me thank a number of colleagues and friends for their generous hospitality over the last few days. I'm particularly delighted to be able to give the first talk because I'm going to give an old-style talk to sort of preface the more cutting-edge stuff that's coming along. It's a very foundational, the main topic, the main advance, as I would see it, is a subjective Bayesian rethinking of issues in model uncertainty in the large. And I'm going to just spend 5 minutes talking about that, and then I'll give you a bit of a story as to how I came to this particular problem area. And then I'll talk about how I think we can solve the problems in that area, at least some solutions, and give you a few examples. I'm quite interested in time series, particularly in econometrics and finance, so we'll be thinking about forecasting in a time series. And the issues that we'll focus on are those that arise when we have a collection of models. More generally, a collection of forecasts, all in terms of distributions. We're all Bayesians, so we forecast in terms of subjective probability distributions. Issues arise then in comparing models, comparing forecasts, calibrating each one individually against the data, and then combining in order to make inferences and decisions based on those inferences. Well, a year or two ago, I ran into some new ideas that other people were publishing. I'll refer to these as new methods of combining sets of density forecasts. This is terminology that comes from the Bayesian, well, it comes from the econometric literature, where Bayesian methods are being used, decision theory as well as Bayesian statistics, belief analysis, to put together forecasts, distributions from several models, bring them to data and show that they can improve on everything probability tells us to do, Bayesian model averaging in particular. So I looked at these a little bit. I'll tell you about them as we go through. And I needed to understand what they were, why these methods were working. I needed to go back and try and understand them from a subjective Bayesian point of view. And that's really the main content of the talk today. So we all know how to do probability theory. We follow the rules. Bayesians follow the laws of probability. That's all we do, right? Well, the decision theory complements it, the yin and the yang of Bayesian analysis. This is a picture from one of our books or one of our papers a few years ago of, on a time axis of a set of 6 posterior probabilities on 6 models as you move through time, being updated by each observation based on how well it forecasts the next observation. So that's BMA, and we'll talk about that later a bit too. Inherently, in a time series context, as you build a model and you look at the data, you forecast one step ahead. It's the likelihood function contributed by that one observation that then updates your prior to posterior. Across a set of models, this gives you model probabilities that change through time. So model scoring in a Bayesian analysis in time series is inherently focused on one-step forecasting accuracy. So in econometrics and a few other areas, we've sort of been thinking about this for a few years because often what we're building models for is other reasons. We're interested in forecasting 1, 2, 3, 4, 5, 12 quarters ahead in macroeconomic contexts. We have decisions, portfolio decisions in financial time series, and it's that is the objective of the analysis. We build models to produce forecasts because we want to make decisions based on those forecasts. We're not only interested in one-step forecast accuracy. Sometimes we're not at all interested in it, okay? And then, as we all know, once we get enough data, eventually model probabilities will favor one model. So your closed set of models is self-limiting. because no one of those models will ultimately prove to be the model you want to carry on into the future. But the posterior model probabilities will begin to tell you there's one that has emerged as the winner. So these are well-known features of standard Bayesian analysis, just following the rules in time series forecasting. And that has led a number of researchers, particularly in econometrics, to think about other things. So let's get some technical details down, and I'll just give you a couple of slides describing some of these other things. A set of models indexed by J. So in my example, I'll have J equals 4 models. We'll talk about time series, so I'll be forecasting a time series in the example. But let's just step back and be theorists first. Y is an outcome we're forecasting. Each of the models gives a forecast. Each of the models gives a forecast for Y. So this is generic, the density of Y on that model. I'll use the term H sub J, H for information. Okay? Model J gives me a density function for Y. That, for me, is information. Each of the models gives me a density function. And capital H then denotes the set of information that is generated by those models. This is just notation. Okay, 2 slides on other people's work. Some of the work that set me, well, what it did, it helped me look back at something I did 20 years ago, 25 years ago, and rethink it. A number of authors and papers, I have one paper and a manuscript that I can give people that are interested, have been putting together forecast densities by something that looks like Bayesian model averaging, but it isn't. They're building what they call density pools, linear combinations of the forecast densities, and they treat the weights not as posterior model probabilities, but as tuning parameters. So with respect to particular loss functions, maybe it's 1 step ahead forecasting or 5 step ahead forecasting, or a realized portfolio measure, they optimize those weights. And in a time series, they can do this repeatedly, linking the optimization over time or just at each time point doing it again. So this is density forecast combination, which has, for over 2, nearly 3 years now, become an identified field of econometric research. And a lot of empirical examples show that it beats standard probability-weighted model averaging, standard Bayesian model averaging. A second phase of that, and this is over the last 18 months, mainly from the Bank of England research group. There's a good solid core of Bayesian work being done in all of the central banks in Europe, most of the central banks in Europe, as well as in the US and Japan. They've been doing the same thing, but there's a difference. The difference is that the weights depend on the outcome. So it's outcome-dependent density pooling. It's kind of weird when you first look at it. Well, if you don't know what the outcome, you don't know the weight. Well, just make sure that's a density. The WJ terms have some functional form over Y with some parameters that are then treated as parameters to estimate or to choose to optimize some expected utility function. So is this Bayesian analysis? Is this part of decision theory? The yin of Bayesian analysis, sorry, the yang of Bayesian analysis, or is it part of belief analysis, statistical inference, which is the yin? Or is it just that smart people do smart things? They're building empirical models and fitting them to data, and in a number of empirical examples showing they can work. So I got interested after a number of conversations with this group in particular in trying to understand whether there's a purely subjective Bayesian framework in which that is legitimate. That is, in fact, a distribution that a subjective Bayesian can use. Okay? And that's the theme of the talk. So let's go back to basics and ask where these model forecast densities come from. So far, the first 5 minutes, we've been imagining that I've got a set of models. I have 4 models, or 4,000 or 400,000 models, and they're each producing a forecast, and I want to put them together. Well, there's another context in which you could have a set of forecast distributions, And this has been called variously the expert opinion or agent opinion context, where several of my friends and colleagues tell me what they believe about why.
Are they all your colleagues?
This one is my mum. This lady I have yet to meet, but I understand that I'm going to meet her at the cocktail party. And I have a few reals in my pocket to prove it. So the agent opinion or expert opinion framework is that's a label for a body of literature that cuts across a number of fields: economics, management science, other fields, back almost 40 years. And a number of Bayesians in the 1980s and 90s, really driven by the foundational work of Dennis Lindley, did a lot of work on this general question of, well, what if my friends tell me what they believe about the future in terms of probabilistic predictions? What do I do with that? Okay, that's why I call these densities H. H is information. So when I get those model-based forecasts or forecasts from my community of advisees, I receive information H. I'm a Bayesian. That's data. I need to process that data. I have a prior before I see that data, so what I want is my posterior. Okay? It's very simple. We follow the rules. Follow the laws of probability. This is a strange kind of data. It's a set of distributions. It's a set of functions. Y could be a 40-dimensional financial time series, vector of financial time series indices. Okay? So I got to model the relationships between these curves based on what I know about where they came from. Well, I know these people. These are my friends and colleagues. Or I know these models. I've been building these models. I know about their interdependencies at some sort of global level. But I'm not going to write down a likelihood function for H given Y and do Bayes' theorem. It's way too hard. Conceptually, it's mind-blowing. Well, back in the late 1990s, in a series of papers that were published mainly in the Royal Statistical Society in the early 90s, I was interested in this problem. Joe Cross was a student. And we looked at extending work that had been published by Christian Genet and Mark Shervish. It's a very non-parametric Bayesian view. And it asked about minimal specifications in this framework to be able to do anything at all in terms of defining a posterior. There's a big theoretical story here that's not for this talk. I'm sure my chairman won't let me talk that long. Let me cut to the chase. There's a theorem in the later paper that says in this context, under some assumptions, that I'll make a little more clear on the next slide, my posterior is constrained to have this form. So my posterior is constrained to be a convolution of a conditional density for the Y we're forecasting, given a J vector of dummy variables. The dummy variables in the integral, they are latent variables. Okay, that's what we call them when we see a formula like this. These latent variables, the convolution involves the product of the J densities. Okay? Take your cell phone out and photograph that equation. You don't need to, it's going to be on the next 4 or 5 slides. Okay? This is Bayesian learning, not by multiplying a likelihood by a prior, but by integration. By expanding the conversation to include this set of latent variables, and I'll now call them the latent agent states. So I'm going to call the models agents. They could be people, they could be models, okay? Used to be called expert opinion, but that's too loaded a phrase. So let's look at this equation. What does it mean? Think about this extreme, purely hypothetical anchor. Let's suppose that each of my 8 friends in the photographs a few slides ago, each of them comes to me and tells me they know what y is. So each of the h's is a point mass at a value. Model 1 says it's x1, whatever x1 is. Model 2 says it's x2, and so on and so forth. In that case, this integral collapses. And the alpha function, the conditional PDF alpha in this expression, becomes my posterior on that extreme, purely hypothetical anchor. Okay? So think about that. As you vary the x values that these hypothetical perfect predictions could take, you begin to get insight into how you can infuse into this alpha function your views of the relationships between these agents or models. And the examples will make this transparent. To just finish the summary of the theory of where this comes from, I told you there are some assumptions. Let's just look at that. If I take the expectation of this equation over h, so now I'm looking at my prior distribution. My prior, pi, is the expectation of my posterior with respect to the data. So this has to be consistent with my prior, where the expectation moves through the integral, and this function m is a density for this set of agent states that defines what I expect the product of these densities to look like. And that's where you can begin to infuse dependencies. Okay? So if you have two models that you believe are generally positively related, they're giving similar forecast distributions, weighting similar regions of outcome space, then you'd have some positive dependency in those two dimensions in this m function. And specifying a model, completing the story for a methodological point of view, you've got to specify this function here. Obviously, if you specify this, that constrains the alpha function. I'll call alpha a calibration function. And we'll see how that plays in the examples. The historical story is that the theory in these papers starts out by saying, suppose I have a set of constraints. I specify m and I specify pi. And the theorem then shows you that your posterior must be of this form. So it's a subset of all possible posteriors that a subjective Bayesian could have. Okay, there are others that you could have, but this is a subset that already steps outside standard sort of subjective Bayesian analysis. And so we're going to spend some time exploring some examples. Example 1. Well, I talked about degenerate forecasts. Let's refine that theme a little bit. I'm going to be specifying, the series of examples will just specify an alpha function. What I would think about y if I got perfect forecasts from each of the individual models or people, the agents. Well, let's suppose I like these models, or I like these colleagues and friends, and I think they're pretty good. So if model 1 says x1, like y is 3, let me take that value with some weight. If x2 says if model 2 says x2, I like that value. I'll give it some weight. So a first example, the simplest, is to say I like my prior with some weight, and I'll just adapt to the point values, these latent agent states, with some other probabilities. So the A's sum to 1. A mixture of my prior and the point masses. If I choose that, I have to plug it in here, and then when I see the forecast densities, when I see H, we'll do the integration. My posterior has this form. It's a linear combination of the J forecast densities with constant weights. It's a density pool, a linear density pool. But there's a difference. My prior is in there with some positive probability. Okay? There's nothing here that tells me what the A's are or how to get them. So this includes Bayesian model averaging. We're Bayesians. We can do Bayesian analysis. These A's could be posterior model probabilities, but I've got to have my prior in there as well. It covers the case that I mentioned, the first set of cases I mentioned, where econometricians have been using weights as things to optimize, as decision variables. So now we see, from a purely subjective, non-parametric subjective Bayesian viewpoint, that's okay. That's legitimate. They're playing by the rules. We've been able to understand how it arises from a traditional Bayesian viewpoint. So that's example one. It's comforting to know that what we always have done is a nice simple example. Now let's go to example two. The same form of alpha function, a linear combination of my prior with a set of point masses at the latent agent states with a catch. The weight on model or agent J depends on the value, this hypothetical exact value that's coming from that model or agent. Okay? So you see how I'm trying to get close to this idea of outcome dependency, but in a very different way than the sort of empirical econometric modelers have done. So let's plug that in. Let's think about it first. What does this mean? Think about alpha j as a kernel function. Suppose my prior is sitting around 0, and I generally expect model j or agent j to give me forecasts that sit around 0. Okay? Let me choose an alpha function that downweights values away from 0. Okay? So I'm gonna be dubious about whatever I receive from model or agent j if he's too far away from 0. So think about that as a kernel. Maybe I expect agent or model j to be upwardly biased. He's always over-optimistic in terms of how the stock market's going up. He's always giving me a 1% increment a week. So if I got a hypothetical value from him, I'd bias it downwards, okay? And that could come in through the alpha function. So you see why I'm beginning to flesh out the terminology of this alpha here as a calibration function. It's a way you can begin to put in views about, based on what you know of the sources of the forecasts, here just one by one, you can begin to quantify them in a model. Well, if you do that, the posterior has this form. Again, it's a linear combination of the prior with some weights on each of the density functions h1 to hj, but it's different. Those weights are now outcome dependent. The first thing that happens is the outcome dependent calibration term modifies h. So if alpha was pushing to smaller values to correct for an upward bias, that would tilt hj to lower values, and maybe also downweight extreme values. So it's a recalibrated, pj is a recalibrated version of hj. So this is getting close. Actually, this completely covers all of the outcome-dependent linear combination rules that the econometricians have generated in the last 2 years. They've chosen particular forms of the alpha function, and they fit them. They use splines and all kinds of things. They fit them to data. But they've been doing that without knowing that there's a full subjective Bayesian theory behind what they're doing, and move towards it because they're smart people doing smart things. They've discovered particular functional forms of density combination that happen to be justifiable on a foundational basis. But they missed the boat, because this recalibration is being applied to each j separately. There's nothing in that posterior formula that says anything about relationships amongst the models. J might be several 100,000, and these models are all possible linear regressions with 50 covariates. So we have huge patterns of collinearity, multicollinearities. Okay? If they're forecasts from economic forecasters, there's a lot of herding behavior. You may have heard the phrase herding behavior. When you poll people in a professional community, what do they think is going to happen in the economics over the next few months? You know, there's a lot of positive interrelationship between what you receive from the community. There's nothing in the work to date in the literature, in the econometric literature, that well, they speak to it, but they don't incorporate it yet in their models. So we'd like to do better than that. Same formula then, but instead of just xj in here, I'm going to put the full set of latent agent states. So now, in addition to potentially correcting for biases or downweighting extreme values, I can begin to think about the set of agents, the set of models together. Okay? So, for example, if all but one of them give me x values near 0, these hypothetical values sit near 0, and one is way out, I might want to weight that one differently depending on what its label j is. It might be my favorite expert. Okay? It might be somebody I don't know and I'm less interested. Okay? If I get a set of x values that are all very close, and I'm expecting those guys to agree, then I probably want to downweight the fact that there are 3 or 4 of them in that region of outcome space, because the positive dependencies mean redundancies of information. So by putting in the conditional density, in the regression of y on these latent agent states, this full vector outcome dependency, we can begin to see how the context that is giving me this set of densities can be addressed again from a formal prior modeling point of view. The result is similar to the previous slide. Weights on each of the recalibrated densities now depend on the full set of densities. The recalibration function for model J also depends on what I see from all of the other models, okay? And it's by looking at examples, specific examples, that we can begin to see how this plays out. So I'll turn to, let me go there. I've also already mentioned that we can use this to downweight extremes. I'm going to turn to a couple of examples, just a couple of examples of the calibration function, and then, well, one example, and then one bit of data analysis. So here's a simple, this is just a mathematical example, but it really helps. Let's suppose that y is some standardized version of, well, let me say some financial index next Monday. I like to look at financial time series. So it's standardized, and my current prior sits around 0. I'll just take a t-distribution. So everything, the example depends on what the forms are, what the numbers are, but the ideas don't. And let me suppose that I have 2 models. Well, let me suppose they're two individuals who are going to give me their forecast densities. Okay? And in the main, they tend to agree with me in terms of location. So I'll expect them to be centered around 0 as well. And, well, they tend to be too precise. I could take anything there. So we'll take a Cauchy. It has fat tails. It sort of sits around 0. And I know these people, okay? I've played with them before, and they've given me lots of information. We work together. I rely on their information. I'm going to use it. I'm going to condition on it, okay? And I know about how they are related. I've seen their dependencies play out in the past, okay? So we'll have a dependency in this bivariate Cauchy distribution, okay? That m function defines the alpha function, okay? And we can talk about whether you want to do the m to alpha or vice versa. Let's look at some data. This is the univariate marginal distribution in M, this Cauchy distribution for each. This is what I'm expecting to see from each of these agents. That's the density there. Let's suppose this is what I actually get. So they each favor positive values, 2.5, 3.5. They're a bit up in the tail relative to my expectation. Okay, they're pretty far from 0. So what am I going to see when I do a Bayesian analysis here using the formulation we've just introduced? Well, let's start with r equals 0. So I'm assuming that they're not dependent. I'm going to get 2 bits of information. Okay? What I have here is my prior. The blue curve is my prior. The red curve is my posterior under this specification. So it has a mode where my prior is, and it has a mode between 2 and 3 where the two predictions come. And it's weighting my prior more than the combination of those two. Okay, the particular numbers lead to that in this example. Okay. The third curve on here is just 1/3 on my prior plus 1/3 on each of the forecast densities. So it's a standard equally weighted linear abelian pool, just for a reference. Okay. So I prove I can do the calculations. Now let's suppose that over the last year or so, when I've been working with these colleagues or these models, I've come to know that they are very positively dependent. They herd together. Okay? For example, if R was 0.7, I'd get this picture. My prior and the equally weighted linear pool are the same. I'm seeing these two forecast densities that tell me I should be thinking about positive values a little more than my prior. But I know these two there's redundant information. It's not 2 bits of information. They're positively dependent. Okay? Highly positively dependent. So the posterior says, well, downweight that information. It's 1 point something bits, not 2 bits. Okay? So it's very natural that that arises. Whereas the econometricians, with their opinion pooling methods, would be behaving like this. They have no way of getting the dependency into the analysis. Now let's suppose that I've seen these guys over the last year or so forecasting on a weekly basis, and they always disagree. So I'm going to take R minus 0.7 instead of 0.7. What's going to happen? Somebody sketch me the red curve that will arise in that example. Okay, Mr. Yellow Shirt got it right. It's antithetical. These guys disagree. But now they're both disagreeing with me, and they're both saying it's much larger and positive than you think. Okay? When enemies become friends, something strange has happened, okay? So it's a simple example, but the real point is that dependencies matter. And think about applications to the earlier mentioned context when you're dealing with a bank of a large number of models. And you have lots of information on the interdependencies that will allow you to relatively discount information from subsets of models or highlight antithetically sets of information. I'm going to skip to a different example. It's the last example, although it becomes a time series example in a minute, so it's really the 4th of 5. That's the framework. I'm going to take an alpha function that arises from a specification that happens to yield an alpha function, a calibration function that's a normal linear regression, with the possibility that it's heteroscedastic in the agent states as well. So I'm going to get information in terms of forecast densities, whatever they are, whatever my full posterior is. Let's just look at a case where, just look at what happens when we just know the mean and the variance of those forecasts. We can do calculations whatever h is, but let's just look at the mean and variance information. So fj is the mean from model j, and vj is variance. The idea here is that the parameters here are going to deal with dependencies and calibration. And this may deal with issues of diversity of, amongst the agents. So if the x's are really very variable, that could be a function that gets larger, okay? My uncertainty will go up then when I see a lot of disagreement amongst the forecasts. So in that case then, just looking at means and variances, not bothering with full distributions, we see that my posterior mean is a regression on the point forecasts, which allows, people have been using that for many decades, which allows for biases and so forth. The forecaster uncertainty comes in a term in the variance of my distribution, and whatever this is, and this expectation is with respect to the information here, that is then going to add additional dimensions that describe some of how the uncertainty arising from the differences among the H's percolates through to my posterior. We're getting close to models that, well, special cases of that, people have used empirically in different ways. This is the same slide, it's just gone to time series. So now I'm going to go to a time series example, so we need to think about this in a time series framework. So the only difference is that Y, H, X all now have T's, and at each time I'm going to get a set of forecast densities for Y, for the next Y, from each of these models or agents. This is conditional on the history of the world. We're doing this in a sequential context, moving through time. Think about forecasting a financial index on a daily basis where T index is T. The example will be quarterly economic data. So I'm going to give you an example where we use this linear regression formulation, now written in a linear equation. I've added a time index to everything, so the parameters are time dependent. This is a zero mean conditional normal with some variance that is time dependent. So we can think about now the opportunity to build a dynamic linear model where the x's are dynamic latent factors. And each t will receive a set of distributions which are the prior distributions we get for those latent factors over time. Okay, well, we know how to fit latent factor models. We can do that. The latent agent states then other factors, and the t indices on the parameters and the conditional variance of what's left here give us the opportunity to look at time variation in individual biases across these models or agents, as well as time variation in terms of their interdependencies, as they learn from each other, adapting to the Delphi effects. It also allows us to model variation that is residual, that may be dynamic, may be time variable. And these terms, the first and the last terms, allow us to say, well, maybe they're all rubbish, and there's very little action in this piece. That then becomes a question for empirical analysis. So here's the example for the last few minutes. This is US quarterly macroeconomic data. We've published a number of papers in the last few years using several macroeconomic series that are, really there's only 7 macroeconomic series that central banks care about. And inflation is the most important. Well, inflation and unemployment. So this is quarterly US data running from, you can't see at the back. This is the beginning of 2014. This is back in the 1960s. And we'll build a set of 4 models, J is 4, to forecast inflation. So T index is quarters, and we'll be forecasting quarters. It's hard, okay? That's why we spend so much money on research in central banks. So here are the 4 models. The details really don't matter so much, except for those of you that are interested in macroeconomics. TVAIR, time-varying autoregression. So an autoregressive model where the parameters vary in time according to random walks. Residual volatility modeled in standard ways. The first model is an AR1 with a time-varying autoregressive coefficient and some time-varying volatility. The third model is an AR3 with time-varying parameters. The other 2 models are more elaborate. They have an AR3 with three legs of each of the inflation, the interest rate predictor, that's the treasury bill, and the unemployment rate. Okay, so this is a more elaborate, much more elaborate model. And you see the idea. We've got a mix of models here that econometrics would say are interesting. So what we're going to do is we're going to build a model. It's basically become a time series problem now, knowing that it's a purely subjective synthesis of information we are going to receive from these models. It's different than Bayesian model averaging, and we'll compare it with Bayesian model averaging. At each time, the latent variables are going to come in from their distributions. And the analysis we'll now do fits this dynamic latent factor model to estimate the thetas over time, the residual volatility over time, forward filtering, backwards sampling kinds of things come in. But also these latent states. These are now latent factors. Okay, so we'll get a posterior distribution in terms of a big Markov chain Monte Carlo sample that includes the x's. So we'll have the opportunity to look at, given all of the h's and given the y's, what have we learned about the interdependencies amongst these models? Okay? We'll do it in 3 stages. The first few quarters to start up the models. Then the next few quarters, this is the 1980s, to continue in sequential learning 1 step ahead. So we're refitting the MCMC and doing Bayesian model averaging and other things as we go along, and what we now call Bayesian predictive synthesis. And at this point, the beginning of the 90s, do it just 1 step ahead at a time, forecasting and evaluating the forecasts. And we'll be just looking at some pictures to compare those forecasts over that phase. Okay? So this is a warm-up phase for that forecasting activity. It's probably a bit faint at the back, but these are, as we go through time now, these are trajectories at each time. It's a point estimate based on the data prior to and including that time. So it's online filtering in that model. The main point, whether you can see the colors or not, this is what the coefficient in the theta vector on one model, and this is the coefficient in the theta vector on another model. So you see the negative dependence in those coefficients in the later stages. Okay, one goes up, one goes down. That's coming through the collinearity between the predictions that those 2 models are giving. Okay, the H's. Well, whatever they are, let's look at some forecast characteristics in terms of what we really care about. Is this improving forecasting? At each quarter, let's look at 1 step ahead forecasting, and let's look at the variance of that, the standard deviation of that forecast distribution. Let's look at it for each of the models. These are t distributions. Let's look at it, the Bayesian model average standard deviation. That's the standard deviation of a mixture of t's, weighted by dynamically varying probabilities. Let's look at it for, we've got 2 other comparisons in there, just a linear combination with equal weights and a log linear combination. And then the Bayesian predictive synthesis using the model that we just fitted. This curve is the latter. This is the 1 step ahead standard deviation in the Bayesian predictive synthesis. BMA is down here. These are the models. So the analysis has reduced uncertainty relative to standard applications of Bayesian thinking. The predictive distributions are narrower than Bayesian model averaging. They're narrower than each of the models. Down here is the log score, so the log predictive density 1 quarter ahead from each of the models, from BMA, and from the predictive synthesis. This is one of the models. This is another of the models. BMA is in here somewhere. This is a cumulative log PDF, so this is the log likelihood, if you like. And these are all relative to 0, which is the Bayesian predictive synthesis. Okay, so as you go through time, they're decreasing, they're negative, they're getting increasingly negative. Bayesian predictive synthesis is winning in terms of the traditional 1 step ahead log scoring rule. Okay, let's look over here then at root mean squared error. So just calculate the forecast error using the mean of your distribution and find the root mean squared error. Bayesian predictive synthesis is down here. This is sort of point forecast accuracy. This is improving the precision, and this is the amalgam showing that the synthesis analysis is a win-win. I briefly mentioned the dependencies, but I'm getting a 1-minute warning here, so I'm going to skip this. This is just digging into the collinearities amongst the models. I'm getting a set of 4 t distributions from these 4 models at each time point, and this is one way to then interrogate how they are related over time. Okay? We'll have 5 minutes for questions if anybody wants to go into that anymore. I want to spend my last minute on this instead. I started out with some comments about why just following the rules blindly, model averaging in time series using probability theory, is insufficient and sometimes deficient. When your goals are not 1-step forecasting, you have to think a bit more broadly. So let's think about it. Let's suppose I want to forecast inflation 1 year ahead, or 2 years ahead, 1 year ahead. We could do that two ways. I could take the model that I've just described and project it four steps ahead. Or I could ask each of the models to give me 4-step ahead forecast densities and build a Bayesian predictive synthesis model for those. Okay, let's have a show of hands. Who wants to do this? Raise your hand. You're wasting my valuable time here. Who wants to do this? All right, the majority wins. The goal is 4-step forecasting, not 1-step forecasting. I don't care about 1-step forecasting. You know, my boss is the president of the Bank of Japan, and he wants me to tell him what I think about how things are going in the next year if he were to make these decisions now. All right? So the decision drives the modeling. And of course, in this example, we've done both, and guess what? Building the 4-step ahead focus model naturally wins. So the story is the same. I'm out of time. The predictive distributions, the predictions improve uniformly because we're customizing a model to consume information that's targeting the horizon that we want, and we allow for time variation in the relationships between those forecasts and their biases. So that's the end of my talk. The messages are, well, there's some methodological content here. One of the papers is a development for macroeconomic forecasting. Follow the rules. This is just subjective Bayesian analysis. It's all, you know, there's a justification that I started with for the first half of the talk. And it's helping people who are using good ideas, good ad hoc ideas, to recalibrate, modify, and combine sets of forecasts, but to do it properly by following the rules. But it's also a reminder that not to be closed mind. And this is really a comment about myself, because the first time I saw some of this density-dependent forecasting, outcome-dependent density pooling, I was a little bit skeptical because it just looked like curve fitting. I didn't see the subjective Bayesian rationale. I couldn't see a foundation until I spent a few months rediscovering some work I'd done 25 years ago. This is not about group probabilities. It's not really about crowdsourced forecasting. That's a whole separate theme in this general area. It's a context where I am missing. Okay, a collection of individuals are generating information, or a collection of models that, if you want to be neutral and take the Bayesian out of it, then this discussion today doesn't cover that case. I've got a lot of thoughts on that separately, and how this approach to non-parametric Bayesian model combination can be extended in that direction. And this also relates to some older work too, but that's a separate conversation. Last slide. Here are two good friends, two Bayesian synthesizers, Ken and Matt. There are 2 manuscripts. One is on archive and in submission. The other one is about to go up on different pieces of this. 2 PhD students who unfortunately couldn't join us this week. I guess my time is out. Thanks for coming, and thanks for your attention. And I know we're all ready for caffeine, but I'll take as many questions as our chairman will allow.
Well, we've just seen the longer-lasting minute I've ever seen. But I'll hand the microphone for quick questions, and Mike will try to answer for one of the white microphones that is working, like this one. Questions?
So in your toy example, you had correlation between the 2 models, either 0. In your toy example, you had correlations.
It wasn't correlation, Edgy. It was a bivariate Cauchy.
Okay, so you had a dependence. So if you go to the time series context, how you envision accommodating the time dependence with the cross-section dependence in a machine learning type of, you know, because now you have all these models, and you want to learn, you know, you want to get their forecast for tomorrow, but you also can use their dynamics to predict their own behavior. So you're cheating your friends, let's say.
It's already in there. So underlying that conditional linear time varying parameter model are a set of M's that are updated time by time based on the history of the world. It's all in there, but it's for the operational calculation of posteriors as we receive forecast densities at each time. It's only that conditional calibration function that is needed, okay? But there's an underlying joint distribution of y, t, and xt that has all of that inside it already, that's getting continually updated as you go through time. The operational requirement is just the thetas and the volatilities that are derivative of that joint distribution.
We are running out of time. I'm sorry to say that we already will have to need to be very quick at the coffee break. You have to reestablish yourself, refuel in 15 minutes instead of 30 minutes. Otherwise, Steve Scott, who is the chair of the next session, will not allow you in. Thank you very much for coming.